Hi everyone, and first of all, welcome in Krakow. This is a very special place to us, to Aleph Zero, because most of our team is based here. So in particular, we have lots of people on site, and yeah, we would love to talk to you. You can ask questions. You can ask questions about Aleph Zero, about ZK in general, and you would really love to chat. So yeah, I think that's the most important thing here, to just learn new things, learn new people, and build something cool. So we are here for you. And this workshop is devoted to giving you some background on Aleph Zero, on what are our bounties, so that it's easier for you to start hacking, essentially. So we have two categories of bounties. Basically, it's very similar to what was shown in the Venn diagram. And it's essentially a hacker path where you will be using a very specific library for snarks in Rust to do something. And there is a product path where you are free to build whatever you want. And obviously, we will give you some pointers, some ideas. In the last slide, I will link you actually to a larger document where we have some documentation, some ideas, some tips, and so on that will maybe give you some ideas. Right, so let's start with the hacker path. And to explain the bounty, I first need to maybe recall you how privacy is achieved using ZK, using ZK snarks in general. So if you know Zcash, or you know one of the other privacy protocols like Tornado and so on, they're all very, very similar. And the central object in each of these protocols is the so-called shielded pool, or the anonymity pool. This is technically a Merkle tree where the leaves are some kind of nodes. You can think of nodes as some hidden accounts. Okay, so there is a particular account state that is hashed together with some magic crypto stuff, and it lives in one of the leaves of the Merkle tree. So this is technically how the shielded pool works. And when someone is making a transaction, then basically they are updating the state of this account. And this is very similar to blockchains in general, blockchains that are public, where everything is public, except that when you make a transaction, you don't show the state. You normally don't even show what the state transition is. You only show a proof that the state update you made is correct, right? And for that, you need to generate a ZK snark. And the proof, or the relation actually that you prove, consists of pretty much two things. One thing is that the previous node, the previous state that you had, is one of the leaves in the tree. And you prove that the state transition from your old state to a new state is correct. And then your new state is essentially added to the tree. And there is also this nullifier business where you need to kind of revoke the old state, right? So this is the familiar flow. If you don't know that, basically, yeah, I think the starting point is the classical design of Zcash. I think this is where everything started. They came up with it very early on, and it's used in all these privacy protocols. Great. So this is how it all works. And then, what's the challenge here? So the main challenge is that you need to generate these proofs on a user device, which is typically either a browser or a mobile phone. So normally, you don't have desktop clients for crypto applications, for blockchains. So this is for convenience of the users, that you normally use a browser extension like MetaMask, or you use just like a mobile app to interact with blockchain. And well, this is some kind of a limitation, because these devices are not super powerful, and computing proofs, computing snarks is a little bit heavy. So we need good methods, we need good ideas to make this fast enough so that the user is not affected, right? Because if the proving time is like 30 seconds, well, that's a little bit too slow for the user to be happy with how the app works. Great. So, well, how do we make it fast? So we first need to figure out what is slow in this whole proof. And the slow part is typically proving that your previous state is in the tree. So this is essentially a Merkle path proof, basically showing a Merkle path in a tree and proving that this branch is correct. Right. So this is essentially our goal: make proving this kind of statements. There is a particular leaf that has a Merkle branch to a particular root fast. And what we have prepared for this hackathon is a repository with some kind of benchmarks. And these benchmarks are targeted for the web browser environment. So basically, I would say this is the more popular way of, I guess, interacting with the blockchain currently through a browser. And what we are benchmarking is essentially a Merkle proof on a tree which has roughly 2 to the 36 leaves. Okay, so 36 levels if this tree is binary. Of course, you can play with different arities and so on. And this might also change things. What we haven't done, and what we would actually love to see, is this kind of benchmarks also run on mobile. And well, this is also like including the bounty. If you can do that, if you can like set it up, get it running on a mobile, either Android or iOS, that is a great result. Yeah, here in the slide are also some details on the curve that we use, on the hash function. So the curve is something that we would rather not change, other than, yeah, that there is some small maybe decision to be made whether we use this BN256 curve, which is kind of outdated and has some lower security than it was initially understood. And there is this, I would say, more modern curve that you can also use, but it largely doesn't matter. The running times will scale a little bit with the curve, but this doesn't matter to us. What we are kind of committed to is Halo 2. So Halo 2 is a great library. Zcash is using it. It was first developed by the Zcash team. And then many forks of the original repository has been made, including forks that changed the polynomial commitment to KZG, where the original one was the IPA one. So yeah, these are all technical details. If you're interested in that, just go to the repo. The link is here, but also the link is in the last slide, where I have everything together. And yeah, there are also details on what do we really want here, what are the criteria of judging the solutions, and so on and so on. But yeah, I would say, yeah, we just want to make it fast. There are a couple of ways you can do that. You can play with the WASM compilation. You can play with the circuit. You can play with yeah, many different parameters of the circuit that can maybe change the running time. All tricks allowed in general. Great. And also included in the hacker path is, yeah, I would say a technical challenge to implement snark-friendly encryption in Halo 2. So first of all, why do we need it? Why do we need encryption in snarks? So here's the story. There is this issue with all the privacy protocols that if you make privacy completely permissionless, if you don't put any limitations on who can join and who can leave and when, then there is this issue that certain bad actors will use your protocol, as some of you might heard about Tornado Cache, and this is obviously bad. So people have been thinking about all kinds of ideas. How can you prevent this kind of bad actors to use the system, or how can you disincentivize them to not join the privacy pool, to not launder money, essentially. So one of the ideas is to have a party in the system called an anonymity revoker. This is meant to be probably a decentralized committee who, under certain conditions, could decrypt or reveal a trace of a particular party in the privacy pool. Okay, so what the particular user did in the pool, and in particular, how did they leave the pool? And the idea here is that, well, if you have funds that were deposited to the pool, which obviously came from a bridge hack or whatever, so the intention of the hacker was essentially to launder the money in the privacy pool, then it's kind of sensible to just de-anonymize this particular user, okay? Obviously, this is not so easy, and the decision process of what needs to be revealed and what doesn't is kind of complex. But yeah, the technical part here is that we need to add some mechanism to the system that will allow to de-anonymize some users. And the way to do that is essentially for the user to include in every transaction not only the proof that the state transition is correct, but also some details of this state transition. So some details of the call data. And the way the user does that is by encrypting this data using a specific key, the key of the anonymity revoker. Okay? So in order for this to be efficient, it's always good to, instead of encrypting everything with one asymmetric encryption key, just do it in 2 steps. First, generate a symmetric key, then encrypt the key, and then use the symmetric key to encrypt the data. This might sound a little bit confusing. If it does, I'm sorry, but this is actually what happens in every cryptography application that you use. So if you talk to your bank, you've used TLS, or you do essentially everything, then you don't use asymmetric crypto all the time. You just agree on a key using Diffie-Hellman or something, and then you use symmetric encryption, right? This is to make it efficient. So it's the same here. So the challenge is, there are a couple of ideas on how to do symmetric encryption efficiently in a snark-friendly way. Just we want you to implement one of these ideas. And that's essentially the challenge. There are some resources on what you can do. There are some articles that we link, and yeah, the challenge is to implement it in Halo 2. Great. So, are there any questions for this particular part? Because yeah, I imagine this might be a little bit confusing. So what you cannot do here, what would not work, is use AES, right? AES is the standard symmetric crypto encryption that is used everywhere because this is the standard. But obviously, it is not good for snarks because it's not snark friendly. You cannot easily write this particular function as an arithmetic circuit in a particular finite field. So this is why it's maybe not so great, but there are maybe other ideas, maybe other encryption algorithms that can be used. Right. Yeah, and yeah.
I don't quite know what it would be. Would you be open to a slightly different protocol, or should it follow this protocol and only look to optimize it?
Sorry, can you say it again?
Yeah, so the protocol that you've described here and how to provide this in an equal that can be a central party, like if you thought of a different way to get the same properties from the outs, would you be open to it?
Yeah, obviously. I mean, we are open to everything essentially as part of actually both our bounties. It's just good to talk to us before you start hacking. And yeah, we can find a good path for what you can build. And yeah, there are literally 8 of us here today. So yeah, there will be enough of us to basically take any question and answer whatever your doubt is. So yeah, obviously yes. Great. So let me now move to the product path. And here it's also very flexible, and we would like you to just build something that is using crypto for privacy. So you have seen the ZK landscape in the previous talk. It was very nice. And in particular, there was this, this blob of privacy protocols. And I think it's pretty similar to a blob saying client-side proving. Because for privacy, you build snarks that normally hold some secret data. And to do that, you want the particular user to create the proof, because if the proof would be generated by a server, then the user would need to trust the server, right? So this is what we do. We do privacy, and we would like you to build projects that involve some secrets, some client-side prove it. And yeah, there are lots of different ideas. There are some ideas mentioned in the materials that I will link in the last slide. Mostly related to ZK games, I would say. But yeah, we have lots of other ideas. Just talk to us. If you have some idea and would like to refine it, also talk to us. This is probably the greatest way to come up with something cool. When it comes to the tech stack, we are kind of flexible. Aleph Zero is currently using Ink as the smart contract language, but we are building an EVM compatible layer. So we've thought that it's probably best if we allow hackers to use any EVM stack, because it's just simplest, and this is where the tooling is mature and where you can take a particular path that is well understood and has been followed by many already. So you will be able to find answers to your questions and ask us, ask other hackers about some issues that you can encounter. So the stack that we recommend is, the most popular one is writing contracts in Solidity, writing circuits, so defining your relations in Circom, and using Snark.js to generate proofs, essentially. And if you like some other tech stack, but it also compiles to EVM, then that's great. You can use it, and it will be eligible for the bounty. We recommend people to deploy their projects to Sepolia on Ethereum, or you can deploy somewhere else, some other testnet. This is fine with us. Yeah, just use whatever you are comfortable with. So what we have prepared for the hackathon is a very simple repository with an example of an app using this particular stack. So this is actually the link, the QR code, to the repository. And the repository essentially shows you the simplest possible example of an app which has this ZK component, this client-side proving component. And yeah, it's the simplest thing that you can imagine, namely that you as a user can prove that you know a factorization of a particular number that is posted on chain. So there is a challenge posted, a number, and you must show its factorization. Factoring number is hard, so this challenge makes sense, kind of, because the numbers that we allow in the challenge are still quite small, so maybe not so challenging at all, but well, this is just an example. Anyway, what's the project structure? We have three things. One thing is the circuit, another thing is the contract, and yet another thing is the frontend. And we will talk about each of them separately for a little bit. So the circuit, this is the simplest circuit that you can imagine written in the Circom language. So, well, what do we have here? We have three variables, A, B, and C, and some of them are marked input signal, and some of them are marked as output signal. So think of the input signals as secret variables, okay? So we would like the user to submit the proof that they know A and B, but we don't want the user to reveal these two numbers, right? Because yeah, that's what we want to do. The user just wants to prove that they know the factorization without revealing the factorization. That's what makes it fun, and that's what makes the ZK technology actually useful here. So how can we do that? This is essentially the definition of the circuit. It's a very simple one, and I can already mention that this circuit is not entirely correct. That there's some things missing, as we will discuss in a moment. Because this circuit is just checking one constraint, that the two private inputs, A and B, multiplied together give the public input C. Okay? But essentially all the circuits that you will build will follow the same shape. They will be just more complex in what kind of constraints you have. And we have linked some tutorials, some learning materials on Circom that will show you essentially how we can build more complex circuits. Great. Then how is this circuit used? One place where this circuit is used is to generate one particular verifier contract. So if you open the contract directory in the repository, you have two contracts there. One is actually written by a human, by us, and one is written by a program. It's automatically generated from the circuit. And this is called graph16 verifier.sol. And essentially the main method in this contract is called verify proof. And it essentially takes the proof for a particular output and it verifies the proof whether it is correct or not. So inside, if you go into this contract, which I'm not sure I recommend, there are just some calls to EVM precompiles that deal with elliptic curve operations. So the more interesting contract is the one that you write. It's where this verifier is actually used. So here it's very simple. I just show you one particular method in this contract. It's called solve challenge. And well, you just point to a challenge that you want to solve and you provide a proof that this challenge that shows that you are able to solve the challenge. The proof shows that you know these two numbers, A and B, that multiplied together give C. And yeah, there is some particular way how you need to break the proof into parts and how you need to plug it into the verifier. But this is standard and this will be the same for anything you build. So you don't need to like learn why this and yeah, how it works. You can just use the same code essentially. So graph16 is has proofs of constant size. So no matter how the circuit looks like, except for the number of outputs, the proof will be the proof will be of the same size. So yeah, it's also this code will be the same. Great. Then there is a front end, and I would say the most interesting line in the front end is how you generate the proof. Okay, because this is normally the most challenging part. But if you use Snack.js, it's quite simple, I would say. So what you need to generate the proof are, first of all, the two private inputs, in this case A and B. You need something called the proving key, which is generated in a phase called the setup. The setup for a developer deployment of contracts is not a big deal. You just run some mocked setup and it's fine. For a real deployment in production, the setup is actually a big deal if you use graph16 because you need a so-called ceremony for that. So there is a particular secret generated in the setup that nobody should know unless they will be able to generate incorrect proofs. So we need a specific way of generating the setup to make it work. But yeah, we don't care about that here. There are well-known ways to do that. If you use graph16, yeah, you need to use a ceremony. If you use Plonk, then you need a ceremony, but it's universal, so you can probably reuse some other ceremony. And if you use Starks or hash-based snarks, then essentially you don't need any setup. So this is probably something you know, just a reminder. And what this essentially does is runs this WASM binary that is generated by from the circuit. Okay. Again, when you follow the shape of the project, you will just need to edit the interesting parts. You will not need to make it all work. All these details because it's already there. And I guess for the front end there is React used. I'm probably the least the least competent person to talk about React, but I guess there are many experts here, so yeah, I don't feel comfortable talking about React, so I will not. And regarding this circuit and this example, so there are two exercises I would like you to think about. One exercise is quite obvious because there are some constraints missing in the circuit, and the constraints are that both A and B should be larger than 1. Otherwise, you can just factorize as 1 times n, right, where n is a challenge. So it's not very interesting. If you add these constraints, then you cannot use trivial factors anymore. Unfortunately, there is another issue. And this issue you will be able to understand only if you know the details. That the variables, the signal variables, are not like U1 to 8 or U5 to 6, 256, sorry. They are finite field elements. And this changes a little bit things. And you need to be careful because overflows work very differently than overflows on variables you would normally use. So yeah, you can think about it. You can ask us if you don't know the answer, but even if we add these constraints, A larger than 1, B larger than 1, it will be still wrong. Meaning that there will be still a way to cheat the contract, to cheat the verifier. Great. So this is the summary of our bounties. So there is this hacker path, there is this product path. Hacker path is more about working with Halo 2, working with optimizing the browser approval time. Product path is building your own things. We are very flexible. If you have your own idea, just come to us, we can discuss, or just start building because, yeah, there are no hard constraints here in the path. Just build something interesting that has client-side proving. And yeah, this is the QR code which has a document which has all the details mentioned about the bounties, some more information, some materials for the hackers, some documentation and so on. So feel free to just go there and see for yourself. We will also post it on Discord. And yeah, this is the prime source of information for our bounties. And you should talk to us. Because we are here, we are glad to talk to you. And thank you, that's all.